Welcome to chemistry classes. In this video we are going to discuss about bonding in coordination compound. Bonding in coordination compound. Okay, there are different theory to explain there are different type of theory to explain bonding in coordination compound, but scientist Alfred Werner first explained bonding in coordination compound. We know Werner's theory. He explained primary valency, secondary valency, this type of points explained by Alfred Werner. But Alfred Werner failed to explain this type of properties of coordination compound. That's why Werner failed to explain chemical bonding in coordination compound. Okay, Alfred Werner failed to explain why certain elements only make coordination compound. Not all elements do not form coordination compound. Only certain elements forms coordination compound. Similarly here, Werner failed to explain bonds in coordination compound. Bonds of coordination compounds are directional property. The directional property of coordination compound also cannot explained by Alfred Werner. Also here magnetic property and optical property of coordination compound. This property also not explained by Alfred Werner. Okay, that's why later onwards there are many theory formed to explain bonding in coordination compound. Such type of theories are here: valence bond theory, crystal field theory, ligand field theory, molecular orbital theory. These are the different theories introduced by scientists to explain bonding in coordination compound. Okay. So here we have to study here valence bond theory and crystal field theory. So here we discuss Alfred Werner first explained bonding in coordination compound, but it is not completely success. He failed to explain some properties of this type of properties of coordination compound. He cannot explain magnetic property, optical property of coordination compound, directional property of different bonds of coordination compound. Also he cannot explain only certain elements make coordination compound, not all elements. These things cannot explained by Alfred Werner. Okay. Okay, next one we have to discuss here valence bond theory. In valence bond theory, first we have to discuss here basic assumptions in valence bond theory. So let us see here basic assumptions for valence bond theory. Okay, look here. Here this is valence bond theory. Here you can see here it represents central metal atom or central metal ion. Here it represents central metal atom and this represent ligand. And here central metal atom with empty hybrid orbital. It will hybridize with, it will overlap or it will hybridize with filled orbital of ligand. Ligand orbital, it is filled with electrons, and this is metal hybrid orbital, it is empty. Okay, so this empty orbital and filled orbital, they will hybridize. Okay, after hybridize, here one type of bond formed, and we know this is coordinate bond. We learned coordinate bond before. So electron pair donate to empty orbital and form a type of bond, coordinate bond. Okay, so here it represents ligand to metal coordinate bond. Electron pair donate from ligand to metal. Okay, that's why I remark here. And here another point we have to understand. understand here central metal ion or central metal atom or central metal ion make available a number of empty orbital for making coordinate bond. Here we discussed central metal atom with the empty orbital. It will hybridize with paired electrons, paired orbitals of ligand and form a coordinate bond. Here central metal atom, it make available a number of empty orbital. Many empty orbital. Okay, so here central metal atom make available different number of empty orbital to make this type of coordinate bond. For example, here you can see we discussed before coordination compound. Here coordination compound. Here coordination number 4. In coordination compound, we know there is coordination number 4, coordination number 6. Okay, coordination number 4, it will be square planar or tetrahedral, and here coordination number 6 mean it is octahedral complex. So here a coordination compound, coordination number 4. So central metal atom make available 4 empty orbital. Coordination compound, here coordination number 4 mean 4 ligands attaching with central metal atom. It means central metal atom contain 4 empty orbital. That's why 4 different ligands making bond with the central metal atom. Similarly, here coordination number 6. Coordination compound with the coordination number 6 means central metal atom attached with 6 different ligands. It's mean in this type of coordination compound, central metal atom consists of 6 empty orbital. 6 empty orbital. Okay. So here we discuss central metal atom make available different number of empty orbital to make coordinate bond, metal to ligand coordinate bond. Okay. And here another point we have to understand, appropriate atomic orbitals. Appropriate atomic orbitals mean s orbital, p orbital or d orbital of central metal atom hybridized to form a set of orbitals, a set of equivalent orbitals with definite geometry and definite energy. Okay, so here we discuss in central metal atom suitable orbitals such as s orbital, p orbital or d orbital, they will hybridize. Okay, here we discuss central metal atom make available empty orbitals. This orbital may be s orbital or p orbital or d orbital. These suitable orbitals after hybridization, here it form a set of orbitals with a definite shape and geometry. Okay. So after this hybridization you learned before. Okay. After hybridization, these are the possible hybridization: Sp3 hybridization, Sp3d hybridization, dsp2 hybridization, Sp3D2 or D2Sp3. These are the different hybridization formed. Okay, these are the different possible hybridization in coordination compound we have to understand here. Okay, so here empty orbitals of central metal atom, after hybridization it forms a set of orbitals with equivalent energy, or a set of orbital with a definite energy and equivalent and definite a set of orbitals with a definite shape and energy. So here possible hybridization is Sp3 hybridization, Sp3d hybridization, dsp2 hybridization, Sp3d2 and D2Sp3. Also you have to remember, after hybridization you got Sp3. Okay, you got Sp3 hybridization. A coordination compound with the Sp3 hybridization mean it will be tetrahedral geometry. Sp3 hybridization mean tetrahedral geometry. Similarly here sp3d. sp3d mean trigonal bipyramidal. sp3d mean trigonal bipyramidal. DSP2 square planar. DSP2. Remember here sp3 and DSP2 there are 4 orbitals. Coordination number 4 sp3. Look here, one s orbital and 3p orbital. That is sp3. 4 orbital. Okay, so coordination number 4. Also here DSP2, one d orbital, one s orbital and 2p orbital. DSP2 also coordination number 4. Okay, so we know coordination number 4 it forms tetrahedral and square planar. So sp3 it is tetrahedral and DSP2 it is square planar. Okay, DSP2 square planar, sp3 tetrahedral. And here sp3d mean 5 orbitals. 5 orbitals. Okay, so 5 orbitals mean its shape coming like this. Okay, so it will be 1 2 3 4 5 ligands. That is square. It is trigonal bipyramidal. You can see here sp3d, one s orbital, 3p orbital, one d orbital, total 5 orbital. So it will be trigonal bipyramidal. Clear? Last one here sp3d2. sp3d2 means 6 orbital, one s, 3p and 2d. So 6 orbital sp3d2 or d2sp3. Okay, sp3d2, d2sp3 both contain 6 orbitals. They are octahedral. So you remember this hybridization and their structure sp3, sp3d2 and accordingly. Clear? So here we discussed central metal atom with the empty orbital overlap with filled orbitals of ligands and form ligand to metal coordinate bond. Central metal atom make available number of empty orbital. Example here metal with the coordination number 4. 4 orbitals. Okay, a complex with coordination number 4 central metal atom make available 4 empty orbital. Coordination number 6 central metal atom make available 6 empty orbital. Similarly here central metal atom, empty orbitals of central metal atom hybridized to form a set of orbitals. Okay, hybridized orbital. So here we discuss different possible hybridization and their structure. Okay, so here we discussed basic assumptions of valence bond theory. Okay, also here we discuss what type of orbitals involved for hybridization. Also we discuss different type of hybridization and their structure. So look here, based on this we have one problems to solve here. Here 2 coordination compound is given. Okay, so here first one FeNH3 6 times 2 plus, FeNH3 6 times 2 plus, and the second one here FeCN6 2 plus, here first one FeNH3 6 times 2 plus, second one FeH2O 6 times 2 plus. Okay, iron here both coordination compound which contain central metal atom iron. First one here 6NH3 ligand, okay, and second one here 6H2O molecules. Both case central metal atom iron and neutral ligand H2O, it is neutral ligand, NH3 also neutral ligand. Okay, also number of ligands 6. Okay, so both are octahedral geometry. Okay, but here it is given diamagnetic. Here first one FeNH3 2 plus. Here iron it is diamagnetic, and here iron is paramagnetic. Explain this. Why it is why here iron diamagnetic and here why iron here paramagnetic? You know, diamagnetic mean magnetism which contain paired electrons only, paired electron. Paramagnetism mean here substance which contain unpaired electron, unpaired electron. Okay, that is diamagnetic and paramagnetic. So we can use valence bond theory to explain this different magnetic behavior. Okay, so let us see how to explain this. Here you can find the charge of iron. Okay, here you can find charge of iron. Iron it is 2 plus. You know how to find charge of coordination compound we discussed before. For example, you want to find the charge of iron here. So put iron unknown value, it is Y. Okay, and NH3 it is neutral ligand. Okay, equal here outside it is plus 2. So unknown value it will be plus 2. So the charge of iron it is 2 plus, iron 2 plus, Fe2 plus. Similarly you can find the charge of iron here. It is unknown value. You can put any letter x plus 0, x plus 0, H2O it is neutral ligand, charge 0, x plus 0 equal to plus 2. So here charge of iron it is plus 2. So both case iron plus 2 oxidation state. Okay, and here we know iron atomic number 26, 3d6 4s2. Iron atomic number 26. So when you write subshell electron configuration 1s2, 2p6, 3s2, 3p6, 3d6 4s2, outer shell electronic configuration of iron, it will be 3d6 4s2, iron 3d6 4s2. But here iron it is Fe2 plus. Fe2 plus mean we have to remove 2 electron. So 2 electron will be removed from 4s, not from 3d 4s. So Fe2 plus mean it will be 3d6 4s0, 3d6 4s0. Okay, now see here, here this is iron and Fe2 plus. We can use boxes to represent subshell electron configuration. Okay, 3d 4s 4p. Okay, after 3d 4s, next one 4p. Actually 4p here empty orbit, 4p 0. There is no electrons in 4p. Okay, 3d 4s 4p. After 4p it will be 4d. Okay, 3d 4s 4p 4d. These are the subshell electron configuration. When you consider iron, it is 3d6 4s2, 3d6 4s2, 3d6 you can do like this, 1 2 3 4 5 6. Okay, this is 3d6. 4s2 you can do like this. This is 3d6 4s2. Next one Fe2 plus. Fe2 plus mean here 4 0. So there is no electron. Okay. So 1, 2, 3, 4, 5, 6. You have to make all complete. Then only you can pair it. Okay. You have to make it full. Then you have to pair it. Okay. So this is Fe2 plus. Fe2 plus means there is 3d6, no electrons in 4s and 4p. Now let us see here, this is our 2 coordination compound. These 2 common for both this coordination compound. But here this Fe2 plus coming with the ligands. See here, first one FeH2O 6 times 2 plus this ligand. Here 6 water molecule will approach to Fe2 plus. Here you have to understand There are two type of ligands. Okay, in valence bond theory here we have to understand there are two type of ligands. Two type of ligand mean weak field ligand and strong field ligand. I will give you more details about strong field ligand and weak field ligand. Okay, so now you understand there are two different type of ligand, strong field ligand and weak field ligand. Weak field ligand mean when ligand approach to central metal atom, this electron pair do not pair. Pairing do not takes place. But in case of NH3 it is strong field ligand. When this ligand approach to central metal atom, this electron pairs, look here it is already paired. After this 1, 2, 3, 4 unpaired electron. This 4 unpaired electron will be paired. Pairing takes place. If there is strong field ligand, here this unpaired electron, pairing of electrons takes place. I will show you here. Here I told you H2O, it is weak field ligand and pairing do not takes place. Actually here it is Fe2 plus, there are 6 electron. Here H2O, it is weak field ligand, pairing do not takes place. So we have to do like this: 1, 2, 3, 4, 5, 6. So here pairing do not occur. But here NH3 it is strong field ligand. Strong field ligand mean pairing takes place. Here 6 electron, 1, 2, 3, 4, 5, 6. Look here this difference. Here it is weak field ligand. So here electrons, unpaired electrons stay like that. But here strong field ligand, NH3, it is strong field ligand, so pairing taking place. This is the pairing. This is the things you have to understand about pairing. Okay. So here I will give you what type of ligands pairing occur, what type of ligands pairing do not occur. It depends on the strong field and weak field ligand. Okay, when you understand which ligands are strong field ligand, which ligands are weak field ligand, then you can do it easily. Pairing and pairing occur or not depends on these things. Okay. Now see here pairing do not occur, here pairing occur. Okay, here 6 water molecule approach to central metal atom. According to valence bond theory, vacant orbital, these are the vacant orbital. Now these are the vacant orbital, and here in second coordination compound, these are the vacant orbital. So this vacant orbital will hybridize with paired or hybridize with the filled orbitals of ligand. Vacant orbital of central metal atom overlap with filled orbital of ligands and form hybridized orbital. We learned assumptions of valence bond theory, so we discussed that. Okay, vacant orbital of central metal atom hybridize with filled orbital of ligand and form hybridization. Clear? So look here, this is vacant orbital of H2O. So here how many ligands are here? Here 6 ligand. So one ligand will come here. 1, 2, 3, 4, 5, 6. Okay, 6 ligands are coming over here. So which orbital this? This is S orbit, this is P orbit, this is D orbit. Okay, how many orbitals are involving in this hybridization? 1 S orbital, 3 P orbital, 2 D orbital. So look here carefully, 1 S orbital, 3 P orbital and 2 D orbital. Okay, so you can say this is Sp3 D2 hybridization. Here you can see here 1 S orbital, 3p orbital, 2d orbital. So sp3d2, sp3d2 hybridization, sp3d2 hybridization, and it is, we know sp3d2 mean it is octahedral geometry. sp3d2 mean it is octahedral geometry. Clear? So let us check here second case. Here NH3, it is strong field ligand. So here pairing occur. After pairing occur, here first to empty orbital. Here also 6 ligands. One ligand coming here. 1, 2, 3, 4, 5, 6. 6 ligands are coming like this. Okay. So here hybridization occurs here. So which orbital? This is d orbital. Okay, d orbital, 2d orbital, 1s orbital, and here this is p orbital, 3p orbital. So you can say D2sp3. What type of hybridization this? D2sp3. We know sp3d2, sp3d2 and d2sp3 both are octahedral. Both are octahedral. So you can find hybridization. You can find structure of coordination. You can find structure octahedral or tetrahedral, this type of structure, hybridization this way. Okay, if you know which one is strong field ligand, which one is weak field ligand, based on this you can find it. Clear? Our question was like this. Here these are the two different questions. These are the two different ligands. In both ligand iron Fe2 plus, iron Fe2 plus. But here first case it is diamagnetic, second case it is paramagnetic. Why? Look here, in H2O it is weak field ligands, pairing do not occur and there is unpaired electron. There is unpaired electron. So because of this unpaired electron, this coordination compound shows paramagnetic property. But second one, NH3 it is strong field ligand. Strong field ligand and pairing occur. Because of pairing, here only paired electron. So here this coordination compound FeNH3 6 times 2 plus, this coordination compound shows diamagnetic behavior. So based on this way you can find paramagnetic property, diamagnetic property. Also you can find their hybridization, their structure. Clear? Okay, next one we have to discuss here spectrochemical series. Spectrochemical series mean arrangement of ligands according to their strong field and weak field character. Arrangement of ligands according to their strong field and weak field character. This arrangement of ligands called spectrochemical series. So look here, this is spectrochemical series. Here some ligands are given and they are arranged according to their weak field and strong field character. Okay, so look here left part halogens. Okay, here iodine, iodide, bromide, chloride, fluoride. Okay, this is the order, group 7 elements from top to up. Okay, iodine, bromine, chlorine, fluorine, H2O. These are weak field ligand. Halogens are weak field ligands. H2O, it is weak field ligand. Okay, weak field ligand. Okay, also here oxalato. This is oxalato. Okay, till oxalate ligand name we will say oxalato. So here H2O oxalato, halogens, water, oxalate, these are weak field ligand. Okay, here look here, the compound which contain nitrogen generally strong field ligand. Here NH3, NO2, CN, CO, these are strong field ligand. This arrangement of ligands are called spectrochemical series. So NH3, NO2, CN, CO, these are strong field ligand. Okay, halogens, water molecule, oxalate, these are weak field ligand. This arrangement of ligands according to their strong field and weak field character, that is called spectrochemical series. Look here, based on this, we have one more example here. Here, FeCO5 times. FeCO5 times. Okay, so this type of compounds, to solve these things, first you have to know, you have to understand the charge of central metal atom. Here iron, you want to find the charge of iron. Okay, so here carbonyl. I told you in the beginning during naming of coordination compound which ligands and their charges, their charges. So you can revise this video once again. So here NH3, it is neutral ligand, CO, it is neutral ligand, ethylene diamine, neutral ligand, they have no charge. Okay, so here CO, it is neutral ligand, they do not any charge. So here Fe, it is no charge, it is neutral atom here, no charge. Okay, charge of Fe here 0. So here we discussed before iron, atomic number 6. So it will be subshell electronic configuration 3d6 4s2. This is the outer shell subshell configuration of iron. Okay, 3d6 4s2. 3d6 4s2. So here iron, it is neutral atom, no charge, so no need to remove electron. Before, in previous case, iron Fe2 plus we remove 2 electron. Here Fe charge 0, no need to remove electron. So here we have to include 3d6 4s2. 3d6. Okay, first we have to do like electrons like this: 1 2 3 4 5, then 6. Okay, 4s2. Okay, 4p, no electron. But here we have carbonyl. What type of compound? Carbonyl, CO. This is CO. This strong field ligand. CO means strong field ligand. So what happened here? Strong field ligand mean pairing takes place. Strong field ligand mean pairing takes place. So we have to make pairing. Okay. So here total how many electron here? 2, 3, 4, 5, 6. Here 6 electron, here 2 electron. So total 8 electrons you have. So all 8 electrons pairing takes place. So you have to do like this: 1, 2, 3, 4, 5, 6, 7, 8. During pairing, not only 3d electron, all electron you have to take pairing. Here 6 electron, here 2 electron, total 8 electron. So all 8 electrons will be pairing takes place. So here pairing occur. Now see here how many ligands are here? 5 ligands. Okay, now these are the empty orbitals of central metal atom. You have 5 ligands. So here 1, 2, 3, 4, 5. 5 ligands will hybridize with this orbital. Okay, here 1d orbital, here 1s orbital, here 3p orbital. So what type of hybridization this? DsP3 hybridization. DsP3 hybridization mean what type of structure we discussed? Trigonal bipyramidal. DsP3 mean trigonal bipyramidal. Okay, and here only paired electrons. So what type of magnetic behavior here? Diamagnetic. Okay, after ligands came, all pairing occur, only paired electron. So here diamagnetic behavior, and it is DsP3 hybridization. It is trigonal bipyramidal structure. Clear? Okay, next one we have another coordination compound here, FeCl6, FeCl6 3 minus, FeCN6 3 minus. Here first one chlorine ligand, second one here CN ligand. Okay, both contain iron central metal atom. You can find its charge, you can find the charge of each coordination compound. Here you want to find charge of coordination compound. Okay, so you can put any letter Y plus chlorine minus 1. How many chlorine here? 6 chlorine. equal minus 3, equal minus 3. Okay, so y equal to minus 3 plus 6. Minus 1 times 6, it will be minus 6. Okay, when you bring this here, minus 3 plus 6. So answer will be plus 3. So here answer will be plus 3. Okay, so here you can see here iron plus 3 oxidation state. Similarly, you can find oxidation state here FeCN6. Here also Cn minus 1. So same method you can use here, y plus minus 1 times 6, minus 1 times 6 equal minus 3. So y equal to plus 3. So both case you will get iron with the plus 3 oxidation state. Okay. So here the question saying you have two different type of coordination compound, one with the Cl ligand and another one Cn ligand, Cn. Okay, and both contain same central metal atom. But here, but in this coordination compound, iron, its magnetic moment of iron 5.9 Bohr magneton. Second one here iron 1.7 Bohr magneton. So you have two different type of coordination compound with both iron earths plus 3 oxidation state, iron plus 3 oxidation state, but they have different magnetic moment. They have different magnetic moment, one with the 5.9 and another one 1.7 Bohr magneton. Okay, so explain what is the reason. So you can explain based on valence bond theory this different. Okay, so look here iron its oxidation state plus 3 oxidation state. We know general electronic configuration of iron 3d6 4s2. 3d6 4s2, this is the general electronic configuration of iron. Here iron plus 3 oxidation state. Plus 3 oxidation state mean we have to remove 3 electron. 2 electron from this and 1 electron from this. Okay, so we can remove 5 electron. Okay, so sorry, we can remove 3 electron. After removing electron there will be 5 electron. Okay, here Fe3 plus mean we have to remove 2 electron from here and 1 electron from here. 3d6 will change to 3d5. 3d5 4s0. 3d5 4s0. This is the outer electronic configuration of Fe3 plus. Look here, Fe3 plus 3d5. 3d5 mean 1, 2, 3, 4, 5. 3d5 4s0. This is Fe3 plus. Okay, now see here two different type of ligand, Cl and Cn. Use your spectrochemical series. Okay, we already discussed spectrochemical series. Halogens are weak field ligand. Halogens are weak field ligand. Okay, weak field ligand. So here chlorine, it is weak field ligand. Chlorine, it is weak field ligand. So weak field ligand mean pairing do not occur. Pairing do not occur in this case. Okay, so here it will be 6 electron without pairing because it is weak field ligand. All halogens are weak field ligand. So here how many ligands are here? 6 chlorine atoms, 6 ligands. So during hybridization, 1 ligand over here, 1, 2, 3, 4, 5, 6. Okay, so here during hybridization, 1 s orbital, 3 p orbital and 2 d orbital. So what type of hybridization this? Sp3 D2. Okay, so here hybridization Sp3 D2 hybridization Sp3 D2 mean we know it is octahedral. Sp3 D2 and D2 Sp3 both are octahedral geometry. Clear? So Sp3 D2 octahedral. Next one we can find Y magnetic moment 5.9. We know how to find magnetic moment. To find magnetic moment, root of n into n plus 2. Magnetic moment equal to root of n into n plus 2. This is the formula. Root of n into n plus 2. Here n means number of unpaired electron. Number of unpaired electron. This is first coordination compound. Here how many unpaired electron? 1, 2, 3, 4, 5. 5 unpaired electron. So here n means unpaired electron. So 5 into 5 plus 2. 5 into 5 plus 2. Okay. So the value will be 5.9 Bohr magneton. Okay. So you can find magnetic moment very easily. I told you before. Okay, in D block elements, if there is one unpaired electron, 1.7, magnetic moment 1.7, 2 unpaired electron 2.7, 3 unpaired electron 3.7, 4 unpaired electron 4.9, 5 unpaired electron 5.9, 6.9, 7.9. So accordingly you can understand its magnetic moment. Okay, so here 5 unpaired electron, magnetic moment 5.9. Clear? Next one, we have to understand why here Bohr magneton, why here magnetic moment 1.7. So here different ligand, it is Cn. We know Cn, CO, NO2. Okay, this type of ligands are strong field ligand. Cn, it is strong field ligand. So here Fe3 plus actually 6 electron. Actually here 1, 2, 3, 4, 5 electron. But here Cn, it is strong field ligand. Pairing takes place. Okay, 5 electron. 1, 2, 3, 4. Now 4 electron. Now it is 5 electron. How many unpaired electron here? 1 unpaired electron. So you can do accordingly root of n into n plus 2. So here root of 1 into 1 plus 2. Root of 1 into 1 plus 2, answer 1.7. 1.7 Bohr magneton. Clear? So here 1 unpaired electron. So these are paramagnetic substance because it contain unpaired electron. If there is unpaired electron, these are paramagnetic substance. Clear? So these are the reason even both coordination compound contain Fe3 plus one with 5.9 Bohr magneton and another one it is 1.7 Bohr magneton. Clear? Also we can check here hybridization. Here look, after pairing, these are the vacant orbital. We have here 6 ligands. So 1 over here, 1, 2, 3, 4, 5, 6. Okay. So here this is D2. Okay. This is D2 sp3. D2 sp3. D2sp3. So this is also octahedral geometry. Look here, first case sp3d2. Okay, here 4d orbital coming for hybridization. First case 4d orbital coming in hybridization. Okay, this is outer d orbital. This is called outer d. Outside. Okay, here this is inside, inner d orbital. This is inner d orbital involving hybridization. D2sp3 mean this is inner d orbital. You have to understand octahedral geometry. There are two types, inner d orbital and outer d orbital, outer. So sp3d2 mean this d orbital outside, last one. Okay, that's why we will call this hybridization outer d orbital involved in hybridization. Here d2sp3, first d orbital, this d orbital inside. Okay, so in this case inner d orbital involved hybridization. Okay, outer d orbital and second one inner d orbital. So remember, sp3d2 mean sp3d2 outer d orbital, d2 sp3 inner d orbital. Clear? Okay, similarly we have two another compound here, two coordination compound, nickel NiCl4, NiCl4 2 minus NiCN4, here Cl chlorine, here Cn cyano, okay, NiCN4 2 minus. Okay, so you have two coordination compound. In both case you can see here nickel plus 2 oxidation state. In both case chlorine minus 1 charge, Cn also minus 1 charge. So you can find oxidation state of nickel. You want to find the oxidation state of nickel. Okay, both case it is minus 1 and 4 ligands are there equal to minus 2. Okay, so minus 4. Why minus 4? Minus 2. So y equal to minus 2 plus 4. So it will be plus 2 oxidation state. So both case nickel plus 2 oxidation state. Okay, both coordination compound nickel plus 2 oxidation state. Clear? So accordingly you can do 3D 4s, 4p, 4d. Okay, do this. You can draw this one. After that you can fill electron, and here Cl, it is weak field ligand and pairing do not occur. Okay, but here Cn, cyano, it is strong field ligand and pairing occur. Clear? So you can draw it. Okay, draw it and find its hybridization, find its magnetic moment, also find its geometry. You have to get first one sp3 hybridization, tetrahedral, paramagnetic. Here it is weak field ligand, pairing do not occur, so it will be paramagnetic. Second one Cn, strong field ligand, pairing occur and it will be diamagnetic, and it will be dsp2. dsp2 means square planar geometry. Okay, so draw it and practice. Okay, and you can solve more questions. Okay, and watch next video for further information. Okay, so thank you for watching this.